Hi everybody, welcome to another video in Calculus 2. We will go to section 7.6, the Harper rule and the growth rates. So actually in this section, the growth rates is a lot more important than the Harper rule. When we go to the chapter 10 about series and sequence, this will be extremely important. Right, so let's just review. First, the indeterminate forms. For indeterminate form, in particular 0 over 0 and infinity over infinity, because usually for the Harper rule, we need to have the limit of a ratio, so something over something. So instead of indeterminate form, we have 0 over 0 or infinity over infinity. But we extend that into the other form, 1 raised to infinity, 0 to 0, and infinity to 0. So indeterminate meaning that we don't know what it is equal yet, but there's something we can do, and that something is the Harper rule. Right. So one common thing about this, they all have in terms of powers. I should say exponent. So what can we do when we have exponent? Well, exponential function and logarithmic function that inverse each other, just like the trig and the inverse trig function we did earlier on section 7.5. This, if we have ln of something, ln and e cancel out. Likewise, if we have e to ln of something, that also cancel out. And because when it cancel out, we have to have, for instance, if we put number here, that have to be positive because ln of a negative number is undefined. So in this case, m have to be positive. Right. So logarithmic function and exponential function are inverse of each other. So that's why we can write like this. And then also a common thing that we do a lot is when we have ln of, let's say, m raised to the p power, we can take the power, move it outside as a coefficient. Or we can take the power back in. Right. So those are the things that we can use and we should see in this section because we have the powers or the exponents. Right. So now, of course, the Harper rule will be extremely useful just to find the limits. So now we have the limit of this function, limit of those. Right. So first of all, limit of x to the x. So what's that goes to? Of course, when x go to 0 from the right side, that go to 1. So we know the answer is 1 by the graph. Just need to confirm it analytically without the graph. Right, so first, if we don't know what it is, make that equal to y. So let y equal to this. By the way, this may take some space, so try to write small. First, I will let y equal to that limit. Of course, there are the steps here we can follow that exactly, but like I said, sometimes if we can do that without any formula, just that would be better. So the thing is, when we have powers like this, we try to take the power down, and when we take the power down, this identity is very important. So we're going to need ln, so we can take the power down. So I will take ln on both sides. So we'll take ln of y equal to, I can put ln here, but I can also put ln after the limit, and I will do that. I will take ln on both sides, but put ln after the limit. Right. Now using that identity, we can take the exponent down. Right, all of this correct, but I forgot one important thing. The first rule, actually the first important thing in the Hospital rule is when we're trying to find the limit using the Hospital rule, make sure that it has to be in the indeterminate form, or otherwise we don't need to use the Hospital rule. So I forgot to do that step first. So let's check real quick. When x go to 0, we have x to the x power, so this pretty much go to 0 over 0. So indeterminate of that form. Yeah. Because if it is not indeterminate, we don't need to use the Hospital rule. Just put the numbers in directly, and that's the limit. If it is defined. So yes. So that is indeterminate form, so we can use the Hospital rule later. Right. So we should always do that first. And then we take ln because we continue like we normally do. Right, so we take ln, take out the power, and that's what we have. So that's good. But if we use the Hospital rule, we need to have the ratio, because by standard of the Hospital rule, 0 over 0 or infinity over infinity. But it has to be a ratio. And I say ratio instead of a quotient, because that definitely not a quotient rule. Bottom line is we need a ratio. So how do we do that? So we have a product instead of a ratio. So if we move one of them down to the bottom, change the power to negative, and that will take care of it. Now we will move the x down to the bottom and make that negative. And ln of x will stay on top. Now the x here will be at the bottom, but negative exponent. So this is x to the first, move to the bottom, become x to negative 1. Right? Now we have a ratio, and it is indeterminate. So we use the Hospital rule. So we'll apply the Hospital rule. And so we will have limit as x goes to 0 from the right hand side. Right. What did we do on the Hospital rule though? First of all, the Hospital rule must be in indeterminate form to apply, to use the Hospital rule. And the Hospital rule for a ratio is derivative of the top over derivative of the bottom. And that is not a quotient rule. Once again, derivative of the top divided by derivative at the bottom. So for the first problem, let's just say I'll just have ln of x, take derivative, the Hospital rule, meaning derivative of the top and derivative at the bottom. So indeterminate form, the Hospital rule, derivative at the top, derivative at the bottom. Derivative of ln of x is 1 over x. And derivative of this power rule, we take down negative 1 and original power minus 1, so that's minus 2, and that's a negative, right? Now so it's going to be negative for sure, right? It's negative. Now we have a fraction. If we move the x to negative 2 to the top, if we try to move that to the top, it will be x squared on the top, because from the bottom to the top. So, right? It may be silly, but I think it will help. If we just move that to the top, it's negative for sure, and that to the top become x squared, and then there's no thing at the bottom. Right, x squared over x and negative, so we just have negative x squared over x, and x squared over x cancel out, and so we have negative x. Right, that's easy. Now this is not indeterminate form anymore, just put 0 into it and that's it. So when we have this, and so we just have negative 0 from the right hand side, which is positive, and so this end up being negative 0, but still 0. It's not indeterminate form, so just put in the numbers. If it exists, that's the limit. So we have 0, right? That's not the end of it though. What we have is ln of y is equal to 0. So ln of y is equal to 0. So how do we go from here? So remember, if we have e to the ln, it will cancel out. So from here, what we can do is raise both sides to power e. And e to 0 power is 1. And then we have ln and e cancel out. So y is equal to 1. And of course y is this limit. That's what we let equal to. So this is equal to 1 as we anticipated. Right, try the first part. Next we have this. So this is a classic problem. And we have here limit when x go to infinity, when we have 1 plus 1 over x to the x power. And the application to this is the compound interest and the continuous compound interest. We'll see that in the being cost algebra, maybe in pre-calc. But this is the way we define the natural base e 2.7, 1A2A, 1A2A. But let's not forget, the first thing we do when we try to find the limit is put in the numbers, see what happened. Right, so if I put in a number infinity to this, we have infinity plus 1 over infinity over infinity. there's 1 and I don't know why I put infinity here, sorry. Right, now 1 plus 1 over infinity, that one go to 0 because we have a finite number on the top divided by infinite at the bottom. So I would say when we have a finite number divided by either plus or minus infinity, it's going to be 0. Something that goes to infinity will be 0. So we just have 1 raised to infinity power, and that of course one of the indeterminate form. So if it is indeterminate form, then we can use the L'Hopital rule. Yeah, so this indeterminate form. So we will use the L'Hopital rule. So first, when we have the power like this, it will be helpful if we take ln on both sides. Before we do that, let y equal to the limit we're trying to find. Right. So we take ln on both sides. And just like last time, I put ln right after the limit. Right. So ln on both sides. Now what we can do is, since there's an ln, we can take the exponent, move it outside, right in front of the ln. So I will write this as limit x goes to infinity, and there's x times ln 1 plus 1 over x, because later on we use the L'Hopital rule with involved derivative. So let's just write that x to negative 1 instead. We're going to take derivative later, so it's more convenient to write x to negative 1. Yeah, now the 2 here, that kind of better. Right, so indeterminate check. So it should be in using the L'Hopital rule, but the L'Hopital rule will require to have a fraction. So just like what we did earlier, the x here move to the bottom becomes negative x. Sorry, x to negative 1. Right, that x to the first power move to the bottom becomes x to negative 1. And at the top we have ln. Right. Now that's good. We have a ratio. So we can use the L'Hopital rule. Right, L'Hopital rule. So take derivative of the top, derivative of the bottom. Right, derivative of the top, we're going to use the chain rule here. Ln of something. Derivative of ln is reciprocal function, so we're going to have 1 over something. And then derivative of that. Doesn't matter what it is inside. And then derivative of the bottom though is easy. Just power rule, negative x to negative 2. Right. The top in the parentheses is 1 plus x to negative 1. And so hope I have enough space. Right. Have the ratio. I mean that. Derivative of 1 is derivative of constant is 0. Derivative of x to negative 1 is negative x to negative 2. So that derivative equal to this. At the bottom we have negative x to negative 2, which is very convenient. They will cancel out completely. We just left with that, which is very good actually. No, there's no more L'Hopital rule here, so there's no L'Hopital rule. Only do that once, not here. Sorry. Right, so like I said, that cancel out. That. Now, so we have a new limit. Let's put the numbers in and see what happens. Before we do that, I want to rewrite the x to negative 1 as 1 over x. Right. So x to negative 1, we can write 1 over x. You cannot move x to negative 1 to the top, become x. Cannot do that because we have the plus 1 here. If it is a product or if it is multiply or divide, we can move things around top and bottom. But there's a plus, cannot do that. But we still can do this. Right, now let's put infinity in and see what happens. So we will have 1 over 1 plus 1 over infinity. We mentioned this before. 1 over infinity is 0 because finite divided by infinity is 0. So what we have is 1 over 1 plus 0, which is 1. So bottom line is we have the limit is equal to 1 or y is equal to 1. So y is equal to 1. Right? Of course not. What we have here is ln of y, not y. So ln of y, don't forget that. There's ln. So ln of y is equal to 1. Now to get rid of the ln, we can take raise both sides to the e power like we did earlier. So we have e to ln of y equal to e to the first power is itself, so just e, and the ln and the e cancel out, so just have y equal to e. And y is the limit. That's limit as x goes to infinity of 1 plus 1 over x to the x power is equal to e. So this is the definition of the natural base e. Right. Classic problem. Right, so we'll do a little more of this later, but now focus on the more important of the section, more important part of the section, that is the growth rate. So what do we mean by the growth rate? So now the growth rates. So just realize in this section we only have one subsection and everything else just A, B, C. We should have more. This should be 2, but anyway. So what do we do when we have the L'Hopital rule earlier? Right, so what we actually now is we determine, we will rank this kind of function and see which one go to infinity faster, pretty much. So we have the linear function like 1x, 2x, 3x, like something times x. And then the polynomial function. One thing for sure, within the polynomial itself, x squared is lower than x cubed and then slower. I will not write it yet because we do have a notation for something slower than the other, which is at the end of the section, unfortunately, but that's fine. So now try to see which one go to infinity faster. So obviously 3x cubed will go faster to infinity than x squared because x cubed is bigger than x squared, right? So the bigger the power, the bigger the exponent, the bigger the power. And x squared is faster than x, and x is going to be faster than x to negative 1, and then so on. But because x to negative 1 does not go to infinity. Right. Super exponential or the tower function. The reason we call that a tower function because that go to infinity very fast. Of course, we see that. Let's see what the graph of that function look like. Yeah, so go to infinity very, very fast. Of course, we then also have the exponential function. This is e to the x, but I think it should be more general. So let's change this instead of e to the x. Change this to something. So what do we write? It's fine. Don't worry about it. Let's say the base b to the x. That's better. So, and also if we have 3 to the x, it's going to be a lot bigger than 2 to the x, right? We don't have the notation yet, but for now we just say 3 to the x is faster than 2 to the x, for sure. The bigger the number at the base, the bigger as the whole. And then we have all others. They're going to put all of that here, but in reality, in our situation, we will not have anything that complicated. Right, so we have a bunch of different functions, of course, the ln of x, and then the power of ln of x, and then exponential times ln of x. So there's be a lot of different functions, but we over some important things here. Now the growth rate, and when we talk about the growth rates, we mean when x go to infinity. Of course, it's not going to be x go to negative infinity. When we say growing, x is increasing. So x is increasing. When x go to infinity, the function, it could go to infinity. But what we're interested in here is seeing how fast it go to infinity. Right? Because that's very important. Like I said, when we go to chapter 10, if we got this down, it will be making a lot easier. Right, so let's define things. We have two functions, and we say f grow faster than g if the ratio of g over f of x equal to 0, or equivalently the ratio f of x over g of x equal to infinity. That's kind of difficult to memorize, right? So the bottom line is, think about this as a fraction. If we have something very big divided by something a lot smaller, what do you think we get? So let's say if we have very big function, I should say fast or big, kind of the same thing here. So if we have a big function over something very small compared to it, the whole thing's going to have to be very big, right? So if we have infinity, the top have to be bigger. And if we have something extremely small, something finite, not finite, something small compared to something very big at the bottom, this will be equal to 0. So bottom line is, if the ratio equal to infinity, the top have to be a lot bigger than the bottom. If it is equal to 0, the bottom have to be a lot bigger than the top. So to summarize all of this, the quotient equal to 0. If the quotient equal to infinity, then the top is big. By that I mean the top is bigger, a lot bigger than the bottom, or we say the top goes to infinity faster. That's the proper word for it, but we say a lot bigger than the other function if we compare to. Right, so the quotient equal to infinity, the top is going to be very big, or the top function go very fast to infinity. But if the quotient go to 0, that means the bottom have to be very big. We only have the small amount divided by the huge number. That's going to be 0. So the quotient equal to 0, the bottom is a lot bigger than the top. And by a lot bigger, we mean it grows faster to infinity. Right. And when they divide that equal to m, which is finite, and we call that comparable rates. If m is finite, it could be a finite number, and that is non-zero. Right, so if we have infinity, the top go faster to infinity. If the whole thing equal to 0, the bottom go to infinity a lot faster than the top. If it is equal to a constant anywhere between 0 and infinity, we say they have comparable rates. Right, now compare the row rates of this Ln of x and x to the p. Right, so in that case, just divide them. Right, just pick one, divide by the other, doesn't matter which one which. So we compare the rates of this one, which one go faster to infinity. Right, so I just divide them. When x go to infinity, just take one, divide by the others, like f of x divided by g of x. Right. F of x Ln of x. So if that. Right. Now, first rule when we're trying to find limit is put in the numbers. Maybe if it works, we don't have to do anything else. Right. So put infinity into it. Ln of infinity to p. Notice that in this problem we have p is the natural numbers. Natural numbers meaning 1, 2, 3, and so on. So it's certainly positive. So we have infinity raised to a positive power. It's going to be infinity over infinity. And infinity over infinity, which is indeterminate. So we know for sure that the top goes to infinity, the bottom goes to infinity. We just don't know which one goes faster to infinity. Right, so that's what we're trying to determine here. Both of them go to infinity, but which one is faster? Right, so, and since it is indeterminate form, so we're going to use the Hospital rule. Right, the Hospital rule says take the derivative of the top and then the derivative of the bottom. derivative of ln of x is 1 over x. Derivative of x to the p, that is power rule. We'll take out the p, original power minus 1. Right. Now let's put this as a fraction. When we divide fraction, we multiply with reciprocal at the bottom. So we're going to flip this. Right. Now, what we have here is x, let's say to the first power by default, right? So now we have x to the first, and then x to the p minus 1. What happened when we multiply two things that have the same base? Just add the exponent, right? That's exactly what we do here. There's a p, and then when we add the exponent, we have the base of x. The top, the power, we add them 1 plus p, and then minus 1. 1 minus 1 cancel out. We have limit of x goes to infinity of 1 over p x to the p. Right? So now we change. Let's put infinity in and see what happened. 1 over p, doesn't matter what it is, positive constant, because that's natural number. Right? Let's close. We have infinity to some power. So infinity raised to some power, that is positive, still infinity. So we have the top is 1, the bottom, infinity times something positive, also infinity. So 1 over infinity is going to be 0. So that will make the limit equal to. So limit equal to 0. Now, if limit equal to 0 as a quotient, which one has to be bigger? We have the top divided by the bottom. The whole thing goes to 0, so the bottom has to be very big compared to the top. So in that case, the bottom function is a lot, goes to infinity a lot faster than the top. So let me write this. Since the quotient equal to 0, the bottom has to be a lot bigger than the top. So the bottom function is faster or bigger. So now problem we have g of x. So that function is a lot faster than the top. So our conclusion, the bottom function grows faster than the top. So we go to infinity a lot faster than the top function. Right. We have another example here. This time we have the power function and the exponential function. Right, where p again is a positive real number. So there's a typo here. Please change this to p is in this case actually the natural numbers. So I want to change the prompt, but I changed the wrong prompt. In this case, P is natural number. Don't worry about it. When I post the note online, I'll make this change. Right, so P is natural numbers. That is very important. You see why do we have to change to natural numbers, not just any positive number. Right. Having said that, on the last prompt, it will work if it is any positive number. Doesn't have to be natural number. Right, in this case, it will be natural numbers. Right, so let's just divide them. Like I said, doesn't matter which one which. Right, let's see, what did we left earlier? Earlier we have f of x divided by g of x. So this time let's g of x divided by f of x. Doesn't matter. Let one divide by the other. As x goes to infinity, let's say g of x over f of x. Doesn't matter which. Right, so we're trying to find that limit. G of x, f of x. Before we do anything, let's just put in a number. Maybe we're lucky and we don't have to do anything. So natural numbers, once again, 1, 2, 3, 4, so it's positive. Infinity raised to a positive number. So infinity and infinity. So that is indeterminate. Which means we have to use the Logarithmic rule here. So from that limit, use the Logarithmic rule. So take derivative of the top and derivative of the bottom. And it is not quotient rule. Right, derivative of e to the x is still e to the x, and then derivative of this is p x to the p minus 1. Right. Now, if we put infinity back into this, should have e to infinity and then p x to infinity minus 1, still infinity. So bottom line is we still have infinity over infinity. So which means more of the Logarithmic rule. So we'll take derivative again. Derivative of e to the x. Let's just say e to the x, p x to the p minus 1. Derivative of e to the x is still e to the x. Now the bottom is take down the power, so I p and then p minus 1. And then the power will be p minus 2. And if we can see, just like last problem, this potentially be infinity over infinity. Bottom line is we're going to do a bunch of Logarithmic rule. When everything's settled, we have the top derivative of e to the x still remain e to the x, but the bottom though, we start with p minus 1 and then p minus 2, and if we keep doing that, because it is the natural numbers, it will go to 2 and then 1. And what's that? So we see this in course algebra and pre-calculus. So that is factorial. So the way we define factorial is equal to the product from n back to 0, back to 1. And because 0 factorial is 1. So when we do all of that, we have p factorial at the bottom. So that's why I choose that to be a natural number. So we have this turn out to be factorial nicely. Right. Now, nice thing about this is p factorial is going to be a constant, right? There's no more x at the bottom. So we have e to the x on the top and then p to the bottom. So if we put in infinity, e to infinity over the bottom, there's nothing, it's just p factorial. So we have infinity over a constant, which is infinity. Now if the quotient is equal to infinity, then what is our conclusion? As a quotient equal to infinity, which means the top have to be very big. So the top is very big. So what is the top function? G of x. So we say the top is very big, or more precisely, the top goes to infinity a lot faster than the bottom. So we say g of x equal to e to the x grows a lot faster than f of x. Grow faster than f of x. So we don't have to worry about infinity or 0, which one divided by which, it doesn't matter. If we divide them, and if it is equal to a constant between 0 to infinity, then we say they are comparable rate. Right, so we have the notation that means G is a lot bigger than F. On different like chemistry or physics or more practical science, we say F is negligible compared to G, or even computer science and anything. So that number is too small compared to the other, and we use that simple. But in here, what we say is it grows a lot faster to infinity as x goes to infinity. So in that case, we use that simple. That's simple. And then we have this ranking here. The tower function, of course, we have a tower for a reason. It goes to infinity very fast. So that is the fastest of all of this. That is b to the x. This one is called the exponential function. And we did mention that within that exponential function, for example, 3 to the x is right down 2 to the x. Yeah, so within each class. And then that is the power function. And except for the base b, all of these are positive. So it may be easy to think of those p and q and r and s, all of that equal to 1. So we can let p, q, r, s. So that is the log function. The log function is the smallest. And the logarithmic function is the one that goes slowest. But having said that, that one is still bigger than constant, because a constant does not go to infinity at all, right? A constant stay constant. So we will get back to this in chapter 10. For now, we just have this list. So the one I wrote for the note here is just say revisit in chapter 10. So when we go to chapter 10 about series and sequence, we revisit this. But for now, the tower function is the one that goes the fastest. Faster than exponential. Exponential is faster than power. Power is faster than the log. Log faster than the constant. The constant stay constant, doesn't go anywhere. Right. So with that, I stop the video right here. So that's the end of section 7.6. As always, thank you for watching.